In this video, we look at a systematic way of drawing complex Lewis structures by following a set of 5 rules or 5 steps that we should take. The first of these steps is to sum the valence electrons from all atoms present in the molecular formula. The second is to write the atomic symbols for the atoms involved to show which atoms are connected to which. The third is to complete octets of electrons for all peripheral atoms bonded to the central atom. The fourth requires us to place any leftover electrons on the central atom. And the last rule, if needed, is that if there aren't enough electrons to give the central atom an octet, we must form multiple bonds, either double bonds or triple bonds. These rules are best demonstrated by example, so we will use them to construct a Lewis structure for the polyatomic molecular compound phosphorus trichloride, PCl3. So the first thing we do is sum up all the valence electrons from all the atoms in the molecular formula. And the best way to do this is to use the Roman numeral group number from the periodic table to determine the number of valence electrons for each atom. So we have the molecular formula for phosphorus trichloride as PCl3, which means this molecule contains only one phosphorus atom. If we look up phosphorus in the periodic table, we see that it lies in group 5A and therefore has 5 valence electrons available for bonding. Chlorine sits in group 7A of the periodic table, and therefore each chlorine atom has 7 valence electrons available for bonding. And there are 3 chlorine atoms in the PCl3 molecule, so that represents a total of 21 valence electrons from the 3 chlorine atoms, which gives us a total of 26 valence electrons across the 4 atoms in this molecule. Now, if we're looking at drawing the Lewis structure for a polyatomic anion, for example the nitrate anion, we would need to add the number of the negative charge to this total of valence electrons. So if we had a 1 minus charge on a polyatomic ion, we would need to add 1 electron to the total when summing up the valence electrons. If we had a 2 minus charge on the polyatomic ion, we would need to add 2 electrons to this total, and so on. Along similar lines, if we had a polyatomic cation, for example the ammonium ion, we would need to subtract the number of the positive charge from the total sum of valence electrons. In our case, we have a neutral PCl3 molecule, so we can move forward directly to step 2, noting that we have a total of 26 valence electrons potentially available for bonding that we need to share across the entire PCl3 molecule. Step 2 involves writing the atomic symbols for all atoms involved in the form of a structural formula to show which atoms are connected to which. To do this, we must define a central atom. The central atom is typically the most electropositive atom, or the least electronegative atom. All other atoms will be peripheral atoms. The main exception to this is the hydrogen atom, which being a period 1 element, can only accommodate 2 electrons in its valence shell and can therefore never be a central atom. Hydrogen will always be a peripheral atom and always only be involved in a single bond. We connect the atoms using a single line representing a single pair of bonding electrons, or in other words, representing a single bond. If the molecule contains double bonds, we will address this in step 5. So over on the right-hand side, we've placed phosphorus, the most electropositive element, as the central atom, joined to each of the peripheral chlorine atoms by a straight line representing, at this stage, a single covalent bond. The next thing we do is complete the octets of electrons for all peripheral atoms bonded to the central atom. We do this by adding 3 pairs of electrons to the atomic symbol of each peripheral atom, thereby giving each atom a total of 8 electrons, which of course includes the 2 electrons involved in the single bonds we've already drawn. So, 3 pairs of electrons on that chlorine atom, 3 pairs of electrons on that chlorine atom, and 3 pairs of electrons on that chlorine atom. The exception here is again hydrogen, which can only accommodate 2 electrons in its valence shell. So for peripheral hydrogen atoms, we think in terms of a duet of electrons rather than an octet. And so we do not add any extra electrons to a hydrogen atom, since the 2 bonding electrons represented by the straight lines in the structural formula are the maximum that hydrogen can accommodate. So at this point, 24 of the available 26 electrons have been used so far, which means we still have 2 electrons left over. In step 4, we place any leftover electrons on the central atom, and we do this even if it gives the central atom more than an octet, because as you may recall, 3rd period elements and beyond are allowed to break the octet rule. So we place our 2 leftover electrons on the central phosphorus atoms like so. Step 5 says that if there aren't enough electrons to give the central atom an octet, we need to form multiple bonds. And we do that by using 1 or more pairs of non-bonding electrons from the peripheral atoms. In this case, however, we can see that the central phosphorus atom has 8 electrons in total in its valence shell, 3 bonding pairs of electrons represented by the straight lines, and 1 non-bonding pair or 1 lone pair of electrons. Similarly, we can also note that all 3 peripheral chlorine atoms have 8 valence electrons and also obey the octet rule, with each chlorine atom having 1 pair of bonding electrons and 3 pairs of non-bonding electrons. So in this case, for step 5, we don't have to do anything. This molecule does not have any double or triple bonds, and this structure here is the completed Lewis structure for PCl3, phosphorus trichloride.